Well, good evening. Welcome to Space Oddities. Hope everybody's fine. Thank you for joining us on this Tuesday evening. Sorry, Dave, I was trying to let you in then and my little button wouldn't work, but I'm glad you're here.
Thanks. Thank you. Wait, can you hear me?
Yes, perfectly.
Oh, yes. Okay, good. All right.
Yeah. Anyway, welcome. If you're new here to Space Oddities, thank you very much for joining us. We hope you'll stick around for the fun. And this evening we've got, the usual suspects basically, plus Dave. So hello, Michael.
Hi there.
Roger.
Good evening.
Hello.
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 Governor.
And Dave. How's life, Dave? How are things treating you?
Okay. Let's see. So was I retired last time I talked to you guys? I am now, anyway.
So you've retired?
Well, yeah. I kind of got pushed out. Things are,
right.
Yeah, right. Yeah, being a government worker right now is not.
That's not great.
It's not ideal. So I guess technically I'm on administrative leave, but
right.
Yeah.
Is there any silver lining to it?
Well, yeah, I guess it's not as bad as I expected it was going to be, if that's a silver lining. I mean, I guess, I do miss it. I miss all the stuff, but I maybe not missing it as much as I thought. I guess the silver lining is I get to now spend a lot more time in California with my wife, rather than traveling back and forth quite so much. So
the question is whether she thinks that's a silver lining.
Right. Well, so far so good, but right.
Okay, well, listen, all the best, and I hope everything works out for you.
Thanks.
Right, so this evening, what have we got for you? Well, tonight we've got a bit of a special about radio astronomy, and it's something we've touched on in relation to other things in the past, but we've never really concentrated on it, as it were. So we're going to take you through basically as much as we can about radio astronomy. So we hope you'll stick with us, because obviously it's a really, really important subject. We're going to be looking at the history of radio astronomy. We're going to be looking at some famous radio telescopes, the personalities behind them. Lou is going to be telling us about radio astronomy in planetary science, and lots of other good stuff as well. So we hope that's of interest to you, and that you kick around even if it's not of interest to you. And if it isn't of interest to you, well, it should be, because it's fun. So just the usual housekeeping before we start. Don't forget that you can support Space Oddities by buying us a coffee primarily, and because astronomers' lives matter, of course. So if you can actually scan the link here, scan the QR code, or you can click the link that's just appeared in the chat. You can also, of course, go to the Space Oddities shop. Winter's drawing in, as I've been saying forever now, and you can actually go to the Space Oddities shop, and you can buy your winter hoodies there, and of course t-shirts for next summer, because summer is not far away, he said really optimistically. So you can get all your merchandise there. You can, of course, donate directly to the channel by clicking the super chat icon, which is the one under the chat window with the $sign on it, which will allow you to make a donation directly. And all the money that we receive goes towards keeping the channel running. So your support is much appreciated. Also, don't forget to like, comment, and subscribe. We need the likes, we need the comments, so that YouTube realizes that people are watching what we do, and will boost our presence on YouTube accordingly. So if you could remember to do that, even if you just put hi in the comments after the live stream, that'd be great. Any comments at all, YouTube doesn't care what they are. And like the video as well, if you would be so good. And of course, if you haven't, then we'd love you to subscribe to the channel. We've got about 76% of our viewers at the moment who are not subscribed to the channel. So if you're not subscribed to the channel, it's completely free, of course. And all you need to do is click the subscribe button, and that helps us out with the algorithm as well. So thank you for that. So before we go any further, just a quick word from our sponsor. This video is sponsored by Picastro. It's like Instagram for space nerds. So a big thank you to Tom McCrory and Picastro for sponsoring tonight's show. So without more ado, we're going to go on. And the first thing that we're going to go on to this evening is, quite predictably, today's news. So let me just share this with you. And let's have a look at what's been in the news this week. Let me just get back to where I need to be. There we are. Okay, so I thought we'd take a look at predictably everybody's least favourite thing in the sky at the moment. Well, it's our least favourite thing because of all the nonsense that's been talked about it. That is to say, Comet 3I Atlas. What's going on with the comet? Well, this is one of the very latest images of the comet. It's now past perihelion, which it reached on the 29th of October. And it passed a mere 1.36 astronomical units from the sun. That's 1.36 times the Earth-Sun distance. And now, of course, it's wending its merry way back into interstellar space. Been a few things that have been a bit strange about this comet, but, you know, to be honest, as I've been saying to a lot of people, it would have been really bizarre if this comet had not behaved strangely, because after all, it was born in another star system, very different to our own solar system, probably. So it would have been strange if there hadn't been some anomalies. And of course, anomalies does not mean it's an alien spaceship. But there have been a few strange things. So before perihelion, it really went through a period of unexpected brightening, which is associated with violent outgassing on the comet, which was, you know, again, sort of expected before it reached perihelion as it got closer to the sun. But this was quite a sudden brightening that wasn't quite expected. And its coma turned green, revealing this vigorous activity. Of course, this comet has gone through a few color changes. Not that long before perihelion, it went blue, and then near perihelion it went green again. And the sunward jet, the anti-tail, if you like, which we had seen previously but which had faded a bit, came back with a vengeance. You can actually see the anti-tail, I hope, in this image in front of the comet. It was far stronger than expected. Also, spectra from Hubble, Gemini and the JWST show unusual nickel-bearing compounds, suggesting formation around a chemically distinct star. Now, there's been a bit of a disappointment, and let me explain why. Over immense timescales, the comet's surface endured cosmic ray and gamma ray irradiation, which darkened and reddened its crust, forming organic residues. So basically, over billions of years of cosmic ray and gamma ray radiation, this comet's actually developed quite a thick crust around it. And it was the, if you like, the breaking through of that crust, which is associated with that sudden brightening, that violent activity, where the trapped gases broke to the surface and sort of under pressure, if you like, spurted out. That's probably what that brightening was. But as it neared the sun, that layer sublimated, exposing these volatile ices and triggering the outburst. Now, unfortunately, this irradiation that it's undergone means that the comet is not pristine material dating from its birth billions of years ago, as astronomers had hoped, meaning with chemical analysis, we really stand little chance of unraveling its origins because its surface has been changed. So it's a shame that, you know, by analyzing it chemically, we're not likely to get much of a clue about its origins. But it does explain why this comet has such a high CO2 content, very high CO2 to water ratio, because carbon monoxide molecules irradiated would have been transformed into carbon dioxide molecules by the gamma and cosmic ray radiation. So this at least explains why there's such a high carbon dioxide content. Anyway, it's now receding, it's fading. It's about 1.8 astronomical units away at the moment, and it's offering a fleeting glimpse of matter altered by both interstellar radiation and solar awakening, if you like. It's a rare messenger from beyond our system. It won't be the last, I'm sure. This is only our third known interstellar visitor, but I'm sure there will be others. So you know, we'll be able to, at least I hope in the future, do comparisons between 3i Atlas and whatever 4i turns out to be, because the 3i means third interstellar visitor that we know about. So it'll be interesting to see what 4i is, and there we are. So just a bit of an update on the comet. All the internet nonsense is still raging, and there we are. So what have we got next? Well, I reported earlier this year that there's a plan to build this massive industrial complex right next to the European Southern Observatory at Paranal in Chile. A company called INA want to build a massive hydrogen manufacturing plant there, and this is going to be the size of a small town, and it's only a few kilometers from the Paranal Observatory that you can see here. Now, the Paranal Observatory is there because it's the deepest, clearest, driest, least turbulent skies in the world. And the European Southern Observatory have done a study that showed that light pollution from the project would brighten the night sky above the observatory by around 35%. And the CTA telescope, the new gamma ray telescope that's coming online before too long, that would have its night sky polluted by more than 50%, drastically reducing the observation quality. Also, wind turbulence from the facility's turbines, because they're planning to power this whole plant with, or at least partially with wind turbines, could worsen the atmospheric seeing by up to 40%, while vibrations, dust, and construction activity might damage ultra-sensitive instruments on the extremely large telescope and the very large telescope interferometer. Now, together, these effects would erode Paranal's exceptional darkness and clarity, undermining decades of investment and limiting its potential for major discoveries. The European Southern Observatory emphasizes that renewable energy and astronomy can coexist, but only if large industrial projects are located far enough from key observatories to preserve their scientific integrity. Now, the formal environmental impact assessment process for INA, this big plant, appears to be ongoing. The European Southern Observatory submitted its full report to Chilean authorities, and an executive summary was to be made public, although it hasn't been yet. There isn't yet a public decision confirming whether INA will be relocated, modified, or approved as is. The debate remains between development of green energy infrastructure and protection of astronomical heritage. The clash highlights the broader tension in Chile, balancing ambitious energy and industrial projects with preservation of exceptional natural and scientific resources like Paranal skies. Now, personally, guys, I don't know why the Chilean government just doesn't turn around and say no. It sounds simple enough thing to say. So anybody got any thoughts about that?
Well, they should say no.
Well, yeah. You know, the Chilean government in the past has been fully supportive of astronomy, and they do see it as one of the country's success stories. And now why they would even consider building this massive industrial plant right next to the observatory, I have no idea. Well, you know, money changes hands with these things, doesn't it, I guess? But you know, it would be an absolute tragedy for ESO if this plant were allowed to be built. It's very, very irresponsible.
Isn't there supposed to be some kind of exclusion zone for anything like that around the observatory?
Well, I don't know whether they're supposed to be, but they definitely isn't in Chile.
No.
You know, and you know, I do sympathise. Chile are trying to be green, at least, you know, and attract green infrastructure. But this is not the place to build this plant. It's going to ruin the astronomy at Paranal, and we're going to lose the world's premium telescopes. You know.
Well, look at the money that the observatory brings into the Chilean government.
Well, yeah. So anyway, we'll have to wait and see. The decision rests with the government at the moment. All relevant parties have had their say, so we're just waiting for a decision. It's very sad, you know. It's very sad.
With dark skies around the world, being such a rare and in fact vanishing resource, seems to me
Yeah.
we need some sort of an international agreement to
Absolutely.
maintain
protect-
these
Yeah.
very valuable sites.
Yeah, but
Well, does their impact statement say anything about how far away it would be acceptable? I mean, did they? You said it's just a few kilometers. Is there?
yeah,
You know, is there a distance that's? I mean,
I don't know,
you know.
Dave.
Okay, okay. I just wondered if.
I know the company have been claiming that it won't affect the observatories and they'll do everything they can to limit the light pollution, but it's the size of a small town, for goodness sake.
Right.
So anyway, let's move on to happier things. I'll keep you posted on that one. There's a possibility that dark energy is not speeding up the acceleration of the universe. New evidence suggests that the universe's expansion may no longer be accelerating and could in fact be entering a phase of gradual deacceleration. Now, as you may know, researchers have for a long time used type 1a supernovae as standard candles for measuring cosmic expansion. And they use a set of about 300 to measure cosmic expansion. But what a team have found is that supernova brightness systematically varies with the age of the stars that created them. Younger progenitors produce slightly dimmer explosions, introducing a subtle but crucial bias into earlier measurements. When this effect is corrected, the apparent acceleration of the universe largely disappears. The revised data fit better with models where dark energy weakens over time, implying that its repulsive influence on cosmic expansion may be fading. Independent cosmological indicators such as galaxy clustering and, of course, the cosmic microwave background also align with the evolving dark energy scenario. And in fact, the DES, the Dark Energy Survey Telescope, came up with that conclusion a couple of months ago, that dark energy seems to be weakening. Obviously, if this proves to be true, it's going to mean a profound change in cosmology. And people have already been saying that those who got the Nobel Prize for discovering dark energy should have their Nobel Prizes taken away, believe it or not. So that's interesting, this idea that supernova brightness depends on the age of the star. But anyway, we'll have to wait and see on that one.
Has this been published? I don't think this has been published in peer
it has.
journal.
I was looking at the paper briefly. It's been published. I'll find you a reference later.
Okay, thanks. Love to read it.
Jared Isaacman has been renominated by Donald Trump to be the administrator of NASA to replace interim administrator Sean Duffy. Now, as you might remember, Trump withdrew Isaacman's nomination earlier this year after learning of his donations to the Democrats. The renomination to lead NASA has drawn strong backing from much of the space industry. Many indeed do see his combination of entrepreneurial experience and hands-on involvement in commercial spaceflight as valuable assets for NASA's evolving partnerships with private companies. Supporters highlight his proven record in advancing commercial missions, such as commanding privately crewed flights, and his emphasis on fostering innovation and risk-taking within a framework of accountability. They argue that his leadership could strengthen NASA's collaboration with the commercial sector, expand opportunities for private spaceflight, and accelerate the pace of human and robotic exploration. Some critics, though, are not so happy. They remain cautious about some of his policy positions and his focus on rapid commercial growth. But Isaacman has responded by stressing long-term sustainability, international cooperation, and continued scientific research as central to his plans. He's very much behind NASA science, which is what we need at the moment. Overall, though, the response has been largely positive, with many organizations and experts expressing confidence that his appointment could bring renewed momentum, clearer strategic direction, and a more integrated relationship between NASA and the new generation of private aerospace companies. It's not known why Trump has suddenly renominated Isaacman, having removed his nomination earlier this year, but I guess time will tell. So personally, I think it's great news. I have great confidence in Isaacman to be the person to lead NASA at the moment. couldn't be worse than Sean Duffy at the moment, to be quite honest. But we will see.
The clearest evidence, I think, that he will be good for science would be the not canceling the 50 or so Earth and space missions that are operational, returning good data, and are scheduled for the chopping block. So
yeah,
would love
yes.
to see that.
Yeah, that would be a clear indicator. You're right. So
getting Dave his job back. That's number one.
Yeah. No, sorry. What are we saying? Dave needs his job back.
I don't know if that's going to do it, but thanks, guys. It was pretty government wide that they told everyone in the government, you have to have your butts in your seat every day, and that at that point it became impossible for me to continue, full time. So,
oh, sorry, Dave. But listen, Dave, anything we can do, just tell us, eh?
Okay, thanks.
Okay,
we're going to talk later on today about the Jodwell Bank food bank, I think, right?
Yeah, Jodwell Food Bank. Yeah, absolutely. So what have we got next? Well, this has been in the news this week. There's been a bit of a problem with the Chinese. In fact, a Chinese crew were meant to be returning to Earth from the Chinese Tiangong space station, and their capsule appears to have suffered damage from space debris, and the astronauts were unable to return to Earth on schedule. And it hasn't been confirmed as a debris strike, but that's basically what it looks like. And these events have exposed a critical gap in global preparedness for emergencies beyond the atmosphere. Experts warn that as human spaceflight expands, with multiple nations and private companies sending crews into orbit, there's still no coordinated mechanism for rescue or recovery if a mission fails. They propose the creation of an independent body responsible for developing common safety standards, mission planning, and emergency response protocols. This organization would operate much like an international coast guard for space, ready to coordinate or deploy assistance when astronauts are stranded or in danger. And of course, we British would know that organization as International Rescue. So there we are. The incident serves as a stark reminder that despite advances in launch and habitation technology, human spaceflight remains vulnerable to unforeseen hazards. A formal rescue system, experts argue, is now essential to ensure crew safety as missions become longer, more complex, and more international in scope. Now, I haven't heard the latest about this, what's going to happen, how the astronauts are going to get back. They do have another spacecraft docked with the space station, though, so it's a situation like it was with the Boeing Starliner, where the two astronauts were guests on the International Space Station for longer than intended. There was always a way of them getting back. They were never in any danger. But already, of course, all the popular media, two astronauts stranded at the Chinese space station. They're not stranded. It's just a matter of, it's a matter of organization and scheduling to get them back. But it is a bit worrying if indeed their capsule was hit by a piece of space debris. It would be ironic, in fact, if it were a piece of space debris that came from that satellite that the Chinese intentionally blew up to test as an anti-satellite weapon. That would be a beautiful piece of irony, which scattered countless thousands of bits of space debris throughout low Earth orbit. So we'll have to wait and see with this one. But the astronauts are in no danger. So shouldn't lose any sleep over it if indeed that's what you were going to do. The sun's been a bit active recently. We've had 2025's strongest solar flare, erupting from sunspot AR 4274. It was an X5.1 flare. So the X flares are the strongest and most powerful type of flares. It peaked early in the day and disrupted high-frequency radio communications over Africa and Europe, triggering an R3 level radio blackout. And the sunspot's been particularly active in recent days. It released two earlier flares at X1.7 and X1.2 that were both accompanied by coronal mass injections, or CMEs, And scientists are closely watching whether the latest blast launched the CMI directly towards the Earth. Because AR4274 is currently orientated to face Earth, any related CME could trigger a strong geomagnetic storm and possibly spectacular auroras in the near term. And you can see the flare there, the activity there. So we could, within the next few days, get really, really strong auroras. So you aurora watchers, you could be in for a treat. And lastly tonight, this is a bit worrying. A recent study reveals a major security flaw. A shockingly large amount of satellite-based communications, including voice calls, text, and sensitive government, corporate, and infrastructure data, are being transmitted without encryption. Researchers used a modest commercially available antenna setup to intercept traffic via dozens of geostationary satellites, capturing highly sensitive information with relative ease. Many satellites, particularly the older geostationary ones, were found to be broadcasting data in clear text, i.e. not encrypted, and many companies or institutions sending data through them lacked additional protections like end-to-end encryption. As a result, critical data streams from in-flight Wi-Fi to military and law enforcement communications are exposed and potentially exploitable by anyone with minimal hardware. The scope and accessibility of these vulnerabilities are alarming, implying that hackers could passively eavesdrop on private and institutional communications or actively interfere with systems, possibly compromising security in multifaceted ways. So that is a bit concerning. And you'd think there would be international standards about this, wouldn't you, for data encryption for satellite traffic, but apparently not. So there we are.
Or they have them and they're not being followed.
Yeah, well, that too. Yeah, that's possible as well. So that's all a bit worrying, isn't it? Really. So I hope somebody's. Well, I don't know who would be responsible for this. Again, it's it's international. So I don't know who's actually responsible.
I think this is Alexa's doing. She's always
probably. Blame Alexa. So there you are. So that is the news for this week. I hope you enjoyed that. If you have any questions, viewers, anything you want to say, do put them in the chat. And speaking of which, I'm going to go over to the chat now. Haven't had a chance to see who's around tonight. So yes, I'm here. Well, that's good. That's good to know. So who have we got? Deep Burrito. Hi. Nice to see you. Andy Cowley, good evening. Thanks for being here. Stuart. No, Derek. Derek's not here. Oh, yes, he is. Good evening, Derek. How are you? Sandra's here. Kev's here. Jerry's here. Hi, all. Gerard, thank you so much for your donation, sir. Much appreciated. Derek says, hi, Andy. Glad to see you haven't been washed away with floods. Well, we haven't, Derek. We had one morning last week where it was like night, and we had a few of the most intense thunderstorms I can remember, coupled with tropical type rain. But it only lasted a morning, although it was meant to come back later, it didn't. So we were fine. But Barcelona was quite badly flooded. There were planes and trains cancelled, and stations flooded and all that. But no, we've been fine, thank you. Okay, so Anne's here. Hi, Anne. Nice to see you. Anne Sanderson. Ian's here. Hi. Yeah, you are late again, Ian. I'll have a word with your mother about that. And that's it. So there we are. So thanks everybody for being here. Now we're going to move straight on now with what we're going to talk about for quite a lot tonight, which is our special on radio astronomy. And we're going to start off with Roger. And of course, we're going to ask the question first of all, which is a pretty obvious question. What exactly is radio astronomy? So I'm going to hand over to Roger now to tell us what exactly is radio astronomy.
Ooh, right. Okay. Let me go and get the presentation ready. So, hang on. Share screen. Right. Okay. So, first of all, what is radio astronomy? So let us see what we're all about. Right, can we all see that?
Yep, we certainly can. Let me just
Okay,
another
so
bit bigger. There we are.
okay, right. So listening to the universe's invisible symphony is what the first slide says, and we go back to the start of it in 1932 by a person called Karl Jansky, who was an engineer at Bell Labs, and he was detecting mysterious radio static from the Milky Way center. So he was investigating that and discovered that there was something invisible to the naked eye. And so he started to find out what was going on and what was causing this. But we've got the electromagnetic spectrum here to give you the information of whereabouts we are on the radio waves, which is over towards the right hand side, which goes upwards from the radio waves and microwave and infrared. So we've got increasing wavelengths. So radio wavelengths go from millimeters up to kilometers in their frequencies. So it's quite a variety of frequencies that we will be inspecting. So okay, so how do we pick this up? So we use a big dish. That obviously the bigger the dish, the better the resolution that we've got, and it's all fed down through like we do from when we used to have the old sky dishes. So collect the signals. So it's all filtered down through, and then collected and turned into something which we can absolutely listen to. But originally we were getting some interesting signals, and in '67 we discovered pulsars, and this was by Jocelyn Bell. More on her later on. We've also discovered the cosmic microwave background. So this is the detection of the Big Bang's afterglow, and that's also been discovered through radio astronomy, and also interstellar gas and clouds from the interstellar nurseries here. So things are all forming up quite nicely. So the radio astronomy's cosmic toolbox. So the range we are talking about is 3 kilohertz to 900 gigahertz. So that's the amount of frequencies that we are now using to scour the universe for various types of radio signals that we are able to collect. And Andy will be also talking about a very large array, an ALMA, amongst those telescopes which are actually observing these various lengths of wavelengths for observation. But Karl Jansky, which I'll talk about very shortly, will be has got a very large array named after him, and there are 27 dishes of at least 25 meters in diameter. They span across New Mexico 36 kilometers, and it's been operational for 45 years. So things are
5 years. Blimey, that's
yeah, absolutely. I know. Doesn't time go by when you're having fun?
Doesn't it just?
So we're discovering all these things out in the sky, of black holes and quasars and things that we can't optically see. So things are becoming more apparent to us, although it probably raises more questions than answers, as astronomy does. So we're working out how the observing has created our theories on how the universe's origins have started, and we're still working on it right to this day. So that's a brief introduction on what we have for the what is radio astronomy. We'll go into more about it when we've got some other presentations in the show.
Okay, right. So there we are. As always, viewers, any questions, please put them in the chat. And you're up again, Roger.
Right. Okay. So let me go on to the next one. and we're going to go into more of the people that were involved with making it more understandable for astronomers to know what's going on out there. Okay, so we will get oh sugar, right, nope, no forgiveness, excuse me. Right, so we want a window. Okay, story.
You right there?
Yes.
Okay.
I'm right. Here we go. Right. Da, 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 da. Oop. Hang on. Right. Just getting the right slide up.
It does help. Oh, it's disappeared. Right. Okay. Hang on, Roger's disappeared for a second. Let me just get him back if I can. He's there we are.
Right.
Oh, hang on.
We
Right. Okay. Fine. Go.
right.
Sorry
Okay. So we're
Sorry about the slight pause.
okay. Right. So we're on the story of the radio astronomy. So this is going back to the start of the dawn of a new era. And this is the man, Karl Jansky, the father of radio astronomer. Now, he was working in Bell Labs, born in 1905 in Norman, Oklahoma. And he was son of Cyril Jansky, Dean of Engineering at the University of Oklahoma. He studied physics at University of Wisconsin and graduated in 1927 with exceptional promise. So, here we go. He went to work on at Bell Labs, joined in 1928 at the age of 22, and was investigating sources of static interfering with radio transatlantic communications. He was trying to work out what this interference was. Okay, so this is what he came up with. This is his merry-go-round antenna. So he created this 100-foot wide, 20 feet tall radio sensor. It was mounted on a turntable with Model 4 T wheels, so he could push it round on a turntable. And he was operating this at a frequency of 20.5 megahertz, or 14.6 meters wavelength. Okay. And he was wondering what was causing it, and he thought perhaps it was local thunderstorms, or maybe distant thunderstorms, which was being tracked to down to this unknown steady hiss, which peaked every 23 hours and 56 minutes. So that coincided with sidereal time, not solar time. So he was thinking, uh-oh, this is happening outside, not on the Earth, but outside of the solar system. So, okay, he was discovering radio waves from Sagittarius at the center of the Milky Way. And he put some published findings in 1932 and presented in 1933 electrical disturbances apparently of extraterrestrial origin. So this was the first detection of cosmic radio waves founding radio astronomy. So, initial response was that astronomers largely ignored the discovery's significance, and then he was reassigned at Bell Labs and able to continue his radio astronomy research. That was a bit of a blow, but he died in 1950 at the age of 44.
Oh,
Before things really took off.
Oh,
So that was a bit of a blow.
oh yeah.
But-
to him especially.
But he had someone else sort of take over the mantle. This person called Grota Rober. Ooh, hang on. And in 1937, he managed to build a parabolic radio telescope in his garden. And further on in the 40s, he mapped the Milky Way's radio emissions. and validating, expanding Jansky's discovery. And then after World War II, he helped to establish the radio astronomy as a vital branch of modern astronomy. So he's obviously helped to realize the importance of what was done before him. So we've got the radio flux density unit, which are measured in Jansky units. So he's been recognized as for that reason. So he's obviously been honored with that. And there's a National Radio Astronomy Observatory Award, which is the Carl G. Jansky Lectureship. So, and also preserved is Bell's Holmdom facility preserves a scale model of his revolutionary antenna. So you'll obviously be able to go and see that. So this was another one of the early models of the radio telescopes back in the 40s or so to discover these new founded waves that we are now taking for granted that are now out into the space that we have to look at. So Bell Labs engineer Carl Jansky has was discovered that the transatlantic radio communications were not from the Earth's source, and created that a wave. And the New York Times in 1933 says new radio waves traced to the center of the Milky Way. So he got some front page news on that behalf. But Grote-Rober, who carried on with the pioneering work, he built his telescope in between 37 and 38, and created the first radio map at 160 megahertz, revealing unexpected cosmic sources. So he's managed to overcome the challenges with early magnetrons and receivers ahead of the field, so to be able to achieve some of these things. So static stars to early birds. So 1944 survey was an intense radio emission offset from the galactic center. So there was a 44 survey, and then they've managed to become much more stronger radio sources, transforming the astronomical perspectives and evolving the radio astronomy to a more essential tool for exploring the cosmos. So we've got a basic radio 1944 map of the cosmos here on the left, going out to a more detailed detail on the right hand side, and this is using the 1400 megahertz map. So it's been 80 years from the first map to this time. So it's using the 21 centimeter line, although there are other frequencies that are used to locate other different types of objects that we're now discovering. So it was originally using World War II radar systems that was the basics of it, and was just working on and discovering things and using different frequencies. But solar radio waves, that was discovered in 1946. So that was quite an interesting thing for the astronomy world to look at. So what have we got? So we've got Jocelyn Bell back into the 60s, and she was a Cambridge graduate who detected regular radio pulses at 30 times per second. So, okay. And this is one of the mysterious little green men blocks that she allegedly thought was happening out there, but it wasn't. It was a pulsar. That was what that was. And this is a young Jocelyn Burnell. Burnell at Cambridge University doing some of her instruments, which eventually turned to the discovery of pulsars. So we've discovered over 2,000 pulsars now since 1967, and some of them rotating at hundreds of times per second. and they have proven neutron stars' existence thanks to this radio astronomy. So extreme physics under conditions possible so to recruit on the Earth. Neutron stars, interior structure and composition, so they've managed to do that. Gravitational wave detections and testing relativity, and cosmic distance measuring and timekeeping. So all these things have been expanded on since this radio astronomy are. And here's some of the other telescopes. We've got the Very Large Array in New Mexico, where we've got 27 dishes, using them all together to make it a larger giant telescope. We've also got the ALMA Observatory, which is in the Chilean Andes, and they're going from meter to millimeter wavelengths through all the different wavelengths that they're able to do. So we're using the 21 centimeter hydrogen line. So we're mapping the cosmos using this technique, and hopefully over the next generation we've got OVRO, LWA, and the Square Kilometre Array, which will enable the resolution to go even deeper into what we've got here. So these are the most important people here that we've helped to establish radio astronomy in our lifetimes here. So we've got Karl Jansky, the originator of what was going on out there in the universe, who was then preceded by Grote Reber, who built the first radio telescope in his backyard, and then up to the present time where we had Jocelyn Bell Burnell, who was discovering the pulsars with this revolutionary new aspect of astronomy. Okay, so we've now discovered through radio waves all these new different understandings of how the universe is now expanding, and how we can discover new types of objects and what's happening with our cosmos. And that's what I can say about that.
Thank you very much. Great, Roger. Thank you very much for that. Yeah, it's a fascinating story of the history of radio astronomy. It's become such an important branch of astronomy now that you know it's answering fundamental questions about the universe. And you talked about pulsars. Don't forget that it was the pulsar timing array, measuring the regular heartbeats of pulsars over 17 years, that betrayed the existence of this background gravitational wave hum across the universe, which is at the moment attributed to merging supermassive black holes. There have been some suggestions that they are primordial gravitational waves from the birth of the universe, but I think the opinion has erred on the side of it being the background hum of countless gravitational wave events that are caused by supermassive black hole mergers throughout time. That is this sort of background hum. And all of this would have been impossible without Jocelyn Bell Burnell discovering pulsars and radio astronomy carrying on and using pulsars to detect gravitational waves from those titanic events in the universe. And don't forget also, we have to mention the Event Horizon Telescope, which took the first image of the black hole by using a virtual telescope nearly the size of the Earth to take the imaging radio waves of firstly the supermassive black hole at the center of M87, and then Sagittarius A star at the center of our own galaxy. And again, radio astronomy making absolutely stunning discoveries. And in fact, the Event Horizon Telescope is undergoing major upgrades, and the aim is to give us sort of real-time movies over time of activity around black holes. Now, this would have been unthinkable just a few short years ago, and it's an exciting time for radio astronomy, certainly. Yeah. Okay. Right. Well, what we can do now is move on to Michael, if he's ready. And Michael is going to talk to us about Jodrell Bank, which is a famous radio telescope in England. And it's actually going to be it is the headquarters of the massive project of the Square Kilometre Array, which I'm going to talk about a little later.
Yeah.
It's headquartered in Cheshire in England. And Michael, when you're ready.
Okay. Hold on a second.
I've never actually been to Jodrell Bank. I've passed it on the train. No, I've passed it on the train, but I've never actually been there.
I've been there 2 or 3 times. Yeah.
Oh, I'd love to go.
Yeah. Right. Can you see that? Am I sharing the right
Yeah,
screen?
that's fine. That's fine.
Just hold on. I want. Yeah. Okay. You can still see the main screen. Yeah.
Yeah.
Okay, that's great. Yes, this is about the Jodrell Bank Observatory, its origins, construction, achievements, and legacy. Exploring the history and impact of a famed astronomy centre on its 80th anniversary.
80th, goodness me. Michael is nearly as old as you.
Oh, thank you. This presentation explores the remarkable history of Jodrell Bank from its visionary founder, Sir Bernard Lovell now, through the challenging construction of the 250-foot fully serial radio telescope to its pioneering scientific achievements and lasting legacy in astronomy. Okay, this is the observatory, the telescope in question, the famous 250-foot dish, located on in a rural setting in the heart of Cheshire, in northern England. It was Bernard Lovell who had the vision of the birth of the observatory back in the early 1940s. And this is Bernard Lovell himself. After achieving his PhD from the University of Bath, Lovell moved to the University of Manchester. Lovell's experience with radar technology in the Second World War laid the foundation for his later work in radio astronomy. Lovell was inspired by cosmic rays, motivating his interest in studying celestial radio waves. He envisaged studying astronomical radio waves to explore new scientific frontiers beyond the visible light. Okay. This is the in the beginning they needed to secure a location for the telescope. The university had a horticultural department and botany located in the middle of Cheshire, in a rural location, and this was brilliant for the telescopes. It needed to be in a quiet area in more ways than one. That's the completed telescope as it is today. This is the location of the telescope in the map of England. So you can see that there. That mark there is actually where the telescope is. So planning and building the telescope required innovation, design, and engineering. The observatory facilities were constructed to support advanced research and house the large-scale instruments. This is a picture of the telescope while it was under construction. In the early days, you can see the massive scaffolding there, the steel structure of the dish taking shape, and the mounts, mounting structures on the side of the telescope.
Didn't they actually use, if I remember right, it may be wrong, didn't they actually use steel left over from battleships?
That is one of the things, yes, the actual mountings for the azimuth control on these structures here. The actual mountings for those actually came from a battleship.
That's right. I thought I remembered that. Yeah.
So construction started in the late 1940s, marking a period of innovation and engineering challenges. The telescope's civil engineering work was primarily a collaborative effort led by scientists and technicians, with no single civil engineering company actually identified as the sole builder. Use of lightweight materials was essential to support the enormous movable dish, the structure efficiently. Pioneering techniques were applied to enable the dish's mobility and structural integrity. Okay.
Amazing project.
Oh yeah. The project faced numerous hurdles, including including technical difficulties and financial pressures, logistics, and problems. So unexpected expenses led to budget overruns, requiring reallocation and stricter financial control. Careful financial management and additional fundraising efforts were crucial. A bit like major projects these days, isn't it?
Right. Nothing much changes, does it?
No. Again, a nice image of the actual structure being constructed. 5 years into the construction, into the early 50s, the project was in deep trouble. There had been multiple delays, and the design had to change to meet new scientific challenges. The telescope was virtually complete by 1957, but was hugely over budget, and many had lost faith in the project. Lovell even began to doubt that his vision would ever be realised. But in 1957, something happened, and Sputnik was launched by the Soviet Union, the first artificial satellites. This was the start of the space race, and the eyes of the world turned to the sky. It became apparent that the near-complete telescope at Jodrell Bank was the only instrument in the world capable of locating and tracking the carrier rocket that had launched Sputnik, an intercontinental ballistic missile. Overnight, the fortunes of the telescope changed, and within weeks it was fully operational. So amazing what that can do with an influx of money from the government as well.
Yeah.
The space race wasn't finished there. Jodrell Bank played a key role in the space race, tracking both Soviet and American missions, receiving and sending transmissions, and verifying its success and failure. In 1966, the first images taken from the surface of the moon, transmitted from the Soviet Luna 9 probe, were received at Jodrell Bank. In 1969, Jodrell Bank tracked the Apollo 11 mission, following the descent of the lunar lander Eagle, and listening in as the first humans walked on the moon. This is a track of the descent of the lunar module.
Right.
Surface. It's amazing to see that.
Wow. Do you know, incidentally, which was the first newspaper to break news of Sputnik to the world?
Oh, the Times?
No, it was the Daily Express. What happened was that Jodrell Bank had received the signal from Sputnik, and I don't know why exactly, I can't remember the story, but the Daily Express got the scoop
Right.
before anybody. So news of Sputnik was broken by the newspaper in the UK.
Right. And this is an image of the completed structure as it was in the late 1950s. These are these turrets, if you like, these at the side of the azimuth mounts. These were what came from an ex-British battleship.
Right.
And that.
Oh yeah, you can see that very clearly.
Yeah. Okay. And this is a view of the telescope from the original control room. So, and that's a nice view of that. You used to be able to go and see this controller. I'm not sure about that now. I'm not sure if that's changed now. But anyway, the telescope was fully operational at the end of 1950s. The telescope was built at a cost of over £700,000, equal to over £30 million in today's money.
Whoa.
I know.
Good investment, though.
Oh, yes. Okay. Scientific revolution, while space exploration and national defence captured the headlines, the majority of Jodrell Bank's work has always been dedicated to pioneering radio astronomy, fulfilling Bernard Lover's original vision. Over the decades, the observatory has played a crucial role in discovering and studying phenomena unimaginable back in 1945. Black holes, quasars, pulsars, gravitational lenses, and the cosmic microwave background, the fading glow of the Big Bang. Jodrell Bank has consistently been at the forefront of a revolution in our understanding of the universe. Just like talk a little bit about technology. Jodrell Bank is the centre of the Merlin project, which is an interferometry project by Jodrell Bank that was originally set up in the 1970s. This is what Merlin consists of 7 different telescopes around England and just into Wales, where these telescopes are linked by radio, microwave radio links to form an interferometer. And Merlin is an acronym for the Multi-Element Radio Linked Interferometer Network. It was conceived in the 1970s and became operational in the 1980s. These other telescopes, although the Jodrell Bank telescope is a 250-foot dish, the other telescopes that are linked are 25-meter telescopes in the system. So these telescopes are located at there's a Mark II telescope at Jodrell Bank. There's a telescope at Cambridge, Deptford in Worcestershire, Knockin in Shropshire, and Darnhall and Pickmere in Cheshire. Okay, with this longest baseline stretching 217 kilometres, Merlin operates at frequencies from 151 megahertz to 24 gigahertz at a wavelength of 6 centimeters, brackets 5 gigahertz. Merlin achieves a resolution of 40 milliarc seconds, comparable to the Hubble Space Telescope's optical resolution, making it a powerful tool for high precision radio astronomy.
I think, if I remember rightly, the Cambridge telescope is also linked into the European LOFAR network.
Yes, I believe that's true as well.
Yeah, yeah.
Merlin came along a number of years later. The basic system of Merlin was upgraded to take advantage of super fast optical fiber networks to its headquarters in Jodrell Bank Observatory. It has a unique position in the world with an angular resolution comparable to the Hubble Space Telescope. So it's basically upgraded to the modern optical fiber network rather than the original microwave radio. The telescope itself was renamed to honour Bernard Lovell, and this is one of the early photos of the completed telescope. It was originally called, the telescope was originally called the 250-foot telescope, or the 250-foot Mark I telescope. It was not renamed, and it was renamed the Bernard Lovell telescope in 1987, recognising Lovell's foundational leadership in establishing the observatory. This
If I can just interject there, just a funny story. When I lived in Bristol for a couple of years, and our local secondary school was called the Sir Bernard Lovell School.
Ah.
I don't know whether there was any link locally with him, but anyway, locals didn't seem to know who he was, and all the locals always referred to it as the St. Bernard Lovell School.
All right.
So I did, before he died, I did mean to write to him and tell him he'd been canonized.
Yeah.
Well,
he did go to university in Bath, which is not very far away from Bristol.
Yeah, it could be a link then. Yeah. Oh, indeed.
Yeah.
Anyway, please continue.
So the telescope has been upgraded several times to the structure we see today, and this is the telescope from 2008. A much better looking structure, and definitely better with the whole of the structure painted white as well.
It's a great paint job, isn't it?
Definitely.
Yeah.
Yeah.
That looks great in the sunlight.
Yeah. They probably have to start again when they're finished.
Oh, is that the Fourth Bridge?
Yeah.
Yeah.
Jodrell Bank has a new visitor centre called the First Light Pavilion. The First Light Pavilion was launched on the 4th of June 2022. The architecturally stunning building is at the heart of a £21.5 million project to open up the awe-inspiring heritage of Jodrell Bank to even more people. So unearth the inspirational stories of Jodrell Bank's pioneering scientists in our new permanent exhibition. This is the entrance to the new pavilion. This is a couple of pictures. This is the entrance, sorry, and this is the Space Dome, as they call it. They don't refer to it as a planetarium, although they do planetarium type shows there. I'm not experienced that yet.
Wow, it looks great.
Yeah, so visitors can experience an immersive dome show in our custom-built planetarium style auditorium, the Space Dome, complete with a curved projection screen and 9 digital projectors. So yeah, looks rather technologically advanced. And this is just another nice picture of the telescope to finish off. So thanks very much for that.
Well, thank you very much, Michael. That's absolutely brilliant. So,
Okay.
So yes, Jodrell Bank, and also, of course, there's the new purpose-built building as the headquarters of the Square Kilometre Array.
Yeah.
And that's a beautiful building as well. That opened about 5 years ago, I think, something like that. Anyway, so that's the story of Jodrell Bank. What we're going to go over to now is just going to look at 4 of the modern giants of radio telescope. We've already mentioned all of them. So we're just going to go over to have a look at these giants of radio astronomy as they are. And we're going to start, first of all, with, I just get to the right place. Here we are. Okay, so we're going to start with ALMA, which stands for the Atacama large millimeter. No, I can't remember. It's a millimeter array, basically. It's large millimeter array. That's right. So this receives radio waves at millimeter wavelengths, and it sits in on top of the Chichagno Plateau in the Atacama Desert in Chile. I was a bit wrong earlier, Lou. It's only 5,000 meters. So it was still fairly high up, though. It's one of the highest observatories on Earth, in fact. And, it's put up there because the extreme altitude and dry conditions create perfect viewing conditions for millimeter and submillimeter wavelengths, which are otherwise absorbed by water vapor in the atmosphere. You see, Chile is such a perfect place for astronomy because the skies are the driest in the world. So these wavelengths are not absorbed much by the water vapor in the atmosphere. So it's a perfect place for it. The ALMA itself comprises 66 antennas. They are 12-meter dishes. There are 50 of those, and there are 16 smaller antennas. And they observe at frequencies between 84 and 950 gigahertz, corresponding to wavelengths of 0.3 to 3.6 millimeters. This allows astronomers to observe the cold universe. So ALMA is all about observing the cold universe. And of course, these frequencies are totally invisible to optical telescopes. Now, its scientific mission focuses on imaging cold gas and dust in star-forming regions, protoplanetary disks where planets are born, and distant galaxies from the early universe. It probes the formation of the first stars and supermassive black holes, offering unprecedented insight into cosmic dawn. And it's impossible to overstate the importance of ALMA, because it has the most exquisite precision. When the Event Horizon Telescope captured that wonderful image of the M87 black hole, it was, at least in part, due to bringing ALMA into the array, because it has exquisite precision. And without ALMA, that first image would either have been very, very blurry or just not there at all. So it's a very important telescope. And its origins, just very briefly, it was born from merging the US Millimeter Array and European Large Southern Array in the 1990s. The countries involved included, and continents, Europe, North America, East Asia, and Chile. They all invested approximately 1.4 billion to get this wonderful project working. And it became fully operational in 2013, transforming our view of the cold cosmos. Now, one thing that ALMA has done is to give us amazing images of protoplanetary disks around stars. And here are two of them. As you can see, the star is in the middle of each disk, and the dark rings around are where nascent planets, young planets, are sort of carving their way through the dust and leaving these black rings. And these are obviously direct evidence of planetary birth happening in real time. The telescopes also detected complex organic molecules floating in interstellar space, hinting at the chemical building blocks of life scattered throughout the cosmos. So that's ALMA, revolutionary telescope, and you can see the precision. The one on the left, I can't remember which one the one on the right is, but the one on the left is HL Taury. And when I saw this image, I was just in love. It's an amazing image of this young star system with these planets carving out their paths out of the dust around the young star. Absolutely amazing stuff. So from ALMA, we move to something that we talked a little bit about earlier, VLA, the Very Large Array in New Mexico. And this is at 2,000 or just over 2,000 meters elevation. And it's built, as you can see, in this Y-shaped configuration. And this has become synonymous with radio astronomy since it was first operational in 1981, as Michael said. It was built between 1973 and 1981. It features 27 movable 25-meter dishes that glide along railway tracks, allowing astronomers to reconfigure the array for different scientific needs. Operating across centimeter wavelengths from 74 megahertz to 50 gigahertz, which works out to about 0.6 to 410 centimeters, so very, very wide range. It makes it extremely flexible. And by adjusting these antenna positions, astronomers can balance the resolution against sensitivity, optimizing observations for everything from distant quasars to nearby stellar nurseries. Its research areas include, first of all, black hole jets, detailed imaging of powerful jets erupting from supermassive black holes, revealing how energy travels across cosmic distances. It's also looking at the galactic center, mapping gas motions at the heart of the Milky Way, probing the environment around Sagittarius A star, the supermassive black hole at the center of our galaxy. And also, of course, as we said, looking at planet formation, looking at how planetary systems emerge from clouds of gas and dust. But the VLA continues to study radio galaxies, quasars, pulsars, supernova remnants, cosmic magnetic fields, Uncle Tom Cobley and all. As part of the National Radio Astronomy Observatory, it remains an essential tool for understanding the radio universe. And now we come to what is going to be the granddaddy of them all, the aforementioned square kilometer array. It's the most ambitious radio astronomy project ever conceived, and you can also view it as the biggest scientific project ever built. It was born from discussions in the 1990s, and it's an international collaboration of, I think, 11 or maybe 12 countries at the moment. And the headquarters are at Jodrell Bank in the UK, as we said. Started construction in 2022, and the first observations, the first light for the telescope, due in 2027. So we've only got 2 years to wait. The name derives, square kilometre array, from its enormous collecting areas, thousands of antennas combining to equal 1 square kilometre of radio gathering power. So instead of Jodrell Bank's 250-foot dish, we've got a whole square kilometre of antennae. And these are where they are in Southern Africa. Southern Africa has got the mid-range dishes, 2,500 of them. SKA2 as well, the mid-frequency aperture, 30 million individual elements in South Africa. There are other African countries involved as well. And the great thing about this whole project is that there's a lot of investment not going into the telescope, but also going into schools for STEM education for African children. And there's a big push to get African children into science as a result of the SKA. So that's fantastic. In Australia, at the Murchison Radio Observatory in Western Australia, again a radio quiet zone, is the low frequency aperture. And eventually there will be 3 million antennas there in Western Australia. Absolutely gargantuan project. And this is the genius. Low frequency observations use Murchison in Australia. Mid frequency work centers on South Africa in the Meerkat National Park, where I'm pretty sure you might find a few meerkats. And this maximizes global sky coverage. And operating roughly from 50 megahertz to several gigahertz, the SKA will be 50 times more sensitive than any radio telescope ever built, and survey the sky 10,000 times faster. It promises the highest resolution radio images ever created, transforming our ability to observe the universe at radio wavelengths. The scientific frontier, mapping neutral hydrogen across cosmic time to witness the birth of the first stars and galaxies. So that's exciting that the SKA will be able to look right back to the birth of stars and galaxies in radio wavelengths. Don't forget the James Webb Telescope is looking at the early universe in infrared wavelengths. Well, again, this is going to be another story at radio wavelengths. What are we going to discover? Exciting stuff. Testing gravity, extreme precision measurements to test Einstein's theories and explore fundamental physics. And it's also going to be used for SETI, the search for extraterrestrial intelligence, the most sensitive radio search ever conducted, looking for radio signals from extraterrestrial civilizations. So all this kicking off in 2027. I believe the full SKA is coming online in around 2030, 3 years later. I've been following this project for so long, and I'm really thrilled to see it only 2 years away. First light 2 years away now. Of course, China, not to be outdone, well, they are outdone, but they decided to build an absolute whopper of a telescope called FAST in Guizhou province in China. It's the largest filled aperture radio telescope, finished construction in 2016, twice the size of Jodrell Bank, 500 meter diameter dish, dwarfs all, it's more than that, isn't it? Because it was 250 feet. Anyway, it's a big dish. And, you know, it's bigger than anything ever built before. And you can see it's the scale of this project. I mean, whole villages had to be, if you like, depopulated and told to move on to make way for this enormous structure. Now, this operates between 70 megahertz and 3 gigahertz. That works out to about 4.3 meters to 10 centimeters. So again, a very wide range. It excels at discovering pulsars and mapping neutral hydrogen. Its scientific goals include precision pulsar timing, hydrogen surveys across cosmic distances, and contributing to SETI as well. And it's been an immense success story for the Chinese. Now, if we compare these four, just a brief comparison, ALMA excels at high-frequency millimeter and submillimeter imaging, revealing cold gas and dust in star-forming regions, protoplanetary disks, and distant galaxies. The VLA has got that flexibility with that Y-shaped construction where they can move the antennas backwards and forwards on rails to look at different phenomena. Detailed studies of radio galaxies, pulsars, black hole jets, and cosmic magnetic fields. The SKA promises revolutionary sensitivity and survey speed across low to mid frequencies. That's set to transform studies of cosmic hydrogen, fundamental physics, and the search for extraterrestrial intelligence. And then FAST is a massive single dish, enables deep pulsar searches and sensitive hydrogen mapping, already discovering over 240 new pulsars and probing these enigmatic and so far largely unexplained fast radio bursts with extraordinary precision. So each of these radio telescopes has got its own niche. There's a little bit of overlap, but essentially they're all sort of specialists in particular areas in radio astronomy. And we are entering a golden age for radio astronomy. That these four giants span the electromagnetic spectrum from centimeters to millimeters, each revealing different aspects of our universe, and they are revolutionizing things like our understanding of star and planet formation, galaxy evolution, and fundamental physics. The SKA is going to transform radio telescope with unprecedented scale, speed, and sensitivity. And Fast ALMA and the VLA will continue to make groundbreaking discoveries, almost certainly. But we are at the threshold of a golden age of radio astronomy, peering beyond visible light to unveil the universe's deepest secrets. And this journey has only just begun, to quote a song. So there you have four cosmic giants in radio astronomy. I don't know if anybody's got a particular favorite, but I'm really looking forward to having the SKA online in a couple of years. It's going to be absolutely mind-blowing. So there you are. Okay. Right. Well, viewers, if you've got any comments, as always, let me just take a quick scan through the chat. So there we are.
So Andy, we've been talking about these very large telescopes. You have an extremely large telescope, overwhelmingly large telescope in the optical, these huge radio telescopes. What about the SLT, the sickeningly large telescope? That is in development, is it not?
Yeah. Well, I mean, these telescope names just get ridiculous, don't they? I mean, we've talked many times about this, like the upcoming very large telescopes we've got, and of course the European telescope, the biggest one ever built, was originally, I think, it wasn't going to be called the OWL, the overwhelmingly large, overwhelmingly large telescope.
That was it.
And, but now it's the extra large telescope. So they changed it.
Well, every amateur astronomer knows about aperture envy. So
well, yeah, absolutely. Yeah. Okay. Right.
Aperture is everything.
Yeah. Okay. Well. Lastly, in our section about radio astronomy tonight, we're going to go over to Lou. Lou's going to be telling us all about the fascinating use of radio astronomy in planetary science. So, Lou, when you are ready,
I'm all set. My
okay, right.
my presentation's uploaded. So
okay, take it away.
There we go. Okay, so in the words of a very famous American radio announcer. And now for the rest of the story. But first, here's a little quiz for our audience, just for our audiences. Okay, why are radio telescopes so large? Anybody want to take a guess, or perhaps you know, and put it in the chat?
There we are. Question for you viewers: why are radio telescopes so large? And it's not radio telescope envy. Why are radio telescopes so large? Does anybody know? If you know the answer, put it in the chat. No.
No taker? Well, okay. So it's because radio astronomers are just not very good at small talk.
Oh.
Very good.
Oh.
Taxi for Mayo.
Or could also be because the resolution of a telescope and its ability to see fine detail and to separate objects that are very close together, the spatial resolution or angular resolution is related to the diameter of the telescope divided by the wavelength of the light that you are sensing.
So the Deep Burrito wins that because the Deep Burrito just posted
wavelength. Outstanding.
Well done, sir.
I'm sure we'll be sending you the prize shortly.
Yeah,
it was for the Camaro, I think. So
Sandra says,
we've been talking so far about how you use passive radio astronomy to explore the universe, and for sure, this is a powerful tool. But there is also active radio astronomy that can be used to explore parts of the universe, and we're going to talk about some of those as well. So we're going to talk about how we explore the solar system, just our little region of space here, using radio waves. So
Mike Beer says radio waves have large wavelengths and need large aperture.
There you go. Absolutely right. Absolutely right.
Thank you for that.
Okay. So here's some uses of radio waves in exploring the solar system. This is on the right-hand side here. We see a hemispheric view of Venus as revealed by more than a decade of radar investigations, which culminated in the 1990 to 1994 Magellan mission. And for those of you who remember Magellan, this was a mission to Venus that began with actually a number of instruments on board. And then Congress said, no, too expensive. So they cut it back to one instrument, and that was a radar mapper. The Magellan spacecraft went to Venus as an orbiter. It imaged more than 98% of Venus's surface at a resolution of about 100 meters. We now have mosaics of Magellan images that have some gaps in them. Those gaps were actually filled in by Earth-based Arecibo radar. So here in both cases, we're bouncing radio signals off the surface and timing their return. And you can learn not only about the distance to the topographic feature, but you can learn something about the quality of the surface. So this composite image that you see was produced to improve contrast and to emphasize small features. And of course, was color-coded. Venus doesn't really look like this, but it's color-coded to bring out definition. On the lower on the lower left here, we see a 3D computer model taking this topographic data, and by throwing it into different coordinate transformations, you can kind of appear to be looking kind of across the surface at some of the features of Venus. Okay. I remember before Cassini going to conferences and where we would try to envision what the surface of Titan, obviously I'm talking about Titan today, as I always do, what the surface of Titan might be like. And Voyager was very successful at mapping the atmosphere of Titan, but not so much for the surface because you can't see it in optical frequencies. However, we had ground-based active radar. And the Arecibo, there were Arecibo observations of Titan at about 12.6 centimeters that were signals bounced off the surface of Titan. The echo power is in a diffusely scattered component, okay? But small specular component is present for about 75% of the sub-Earth. In other words, dirt kind of nadir-looking or opposite nadir-looking locations observed. This roughly 13 centimeters was chosen for its ability to penetrate Titan's atmosphere, right? Remember, we said it's opaque and visible wavelengths, and it's only transparent in certain tiny bands in the infrared that are between methane absorption features. But the radar signal can penetrate Titan's thick photochemical haze. So these specular echoes that we see in the upper right here have properties that are consistent with those that are expected for an area that had some liquid hydrocarbons. And we knew that it wasn't hydrocarbon oceans from the echo that was returned, but probably small and large lakes. And in fact, that is what Cassini found. So let's see here. Here we go. There. Okay. So this is a graphic illustrating a technique called radio occultation that is used to probe planetary atmospheres. So here, a spacecraft moves behind the planet or moon, if it has an atmosphere, and sends a radio signal through the atmosphere toward the Earth. As the signal passes through the atmosphere, as it scans down to get vertical definition, it's refracted and absorbed by the atmosphere, causing a shift in its frequency. In other words, a Doppler shift. A radio telescope on Earth, or it could be another spacecraft, you can do it that way as well, receives that signal and measures these changes. And by analyzing the Doppler shift and other signal perturbations, scientists can infer the physical properties of the atmosphere, such as temperature, pressure, and density. And the radio occultation signal that you get at Earth is a function of what we call T over M. So that's the temperature of that level of the atmosphere divided by the mean molecular weight of the atmosphere. So if you're kind of confident that you know the mean molecular weight, then you can get the temperature and vice versa. So let's move on here. Well, for Mars, we have the Perseverance radar imager for Mars subsurface experiment, RIMFAX. And it uses radio waves, to probe Mars subsurface, revealing new features and understandings of Mars evolution that are not visible in other wavelengths. The first ground-penetrating radar set on the surface of Mars. RIMFAX can provide very detailed views of the subsurface structure down to maybe 30 feet, like around 10 meters underground. And so in doing that, the instrument can reveal hidden layers of geology by looking at the echo of the signal that returns and help find clues of past environments on Mars, especially those with conditions necessary for supporting life. And so in other words, we're able to probe the Martian subsurface for water ice. As the rover drives along, the RIMFAX sends out a radio signal into the surface, through the surface. And when the radio waves encounter a new rock layer, or some waves bounce back up toward the RIMFAX, then the RIMFAX detects these return signals, and you can kind of stack them up to get a vertical profile, right? And this builds an image of the subsurface rock layers. The speed of the waves travel through the rock, the speed that the waves travel through the rock depends on the rock's properties, summarized by a quantity called permittivity. And different rock types have different known permittivity values, so scientists can constrain the rock type of each layer. The tilt of the layers can also be observed, and that indicates the conditions that they were deposited in and perhaps geological activity.
Wow.
What's up?
Yeah.
Who knew you could see below the surface? We do this on Earth too, by the way. We've done this at Stonehenge, and we see all kinds of buried bodies underneath the ground in Stonehenge, and so we kind of get a little better picture of what it might have been. One of the ways it might have been used. Well, you can do this from orbit as well. This is an image of MRO, Mars Reconnaissance Orbiter, and it had an instrument called shallow radar, but they call it SHARAD or SHARAD. I think it's SHARAD. This radar is an active radar. It pings the surface of Mars in search of a strong radar return signal that may indicate the presence of underground liquid or something frozen in the first few hundreds of feet, up to maybe a kilometer below the surface. SHARAD probes the subsurface using radar waves with about a 15 to 25 megahertz frequency, and that gets the desired results in the high resolution and the high depth resolution. The radar wave return, which is captured by the SHARAD antenna, is sensitive to changes in the electrical reflection characteristics of the rock, of sand, or any water that may be present under the surface, in the subsurface or under the surface. Water, like high-density rock, is highly conducting, and so it has a strong radar return. And changes in the reflection characteristics of the subsurface caused by layers deposited by geological processes in the ancient history of Mars are also visible. SHARAD on MRO has produced results showing evidence of extensive subsurface ice, very important if we're going to colonize Mars, confirming some Martian mid-latitude glacier-like landforms are actually debris-covered glaciers. This is important because we know there's water ice along with CO2 ice at the poles, but here we're talking about mid-latitude, about lower latitude water reservoirs. Other findings include mapping the internal structure of the polar ice caps, revealing details of lava flows and sedimentary layers, and providing new data on the Martian ionosphere as well, and its interaction with the planet's magnetic field. Okay. Also from orbit is an instrument called MARSIS, the Mars Advanced Radar for Subsurface and Ionosphere Sounding. MARSIS is on the Mars Express orbiter. MARSIS is a subsurface radar with about a 40-meter antenna on the Mars Express orbiter that is searching for water and studying the atmosphere. It's a low-frequency, nadir-looking pulse, now you're just looking straight down, limited radar sounder and altimeter with ground penetration capabilities. So it can not only map the surface morphology, but it can penetrate the surface, and uses synthetic aperture techniques and a secondary receiving antenna to isolate subsurface reflections. The main objective of MARSIS is to look for water from the Martian surface down to about 5 kilometers or 3 miles. I mean, that's really deep. It can characterize the surface elevation roughness and radar reflectivity of the planet and study the interaction of the atmosphere and solar wind in the red planet's ionosphere. And during the lifetime of the mission, the instrument conducts ground penetrating studies over the entire planet. Okay.
Amazing it can penetrate that deep, isn't it? It's quite a depth, 3 miles.
You know, we always say that the universe looks very different depending on the wavelength of light that you look at it in. And of course, now we have gravitational waves, which is a whole other story.
Yeah, absolutely.
But we don't often think about penetrating solid surfaces, right? Penetrating atmospheres, okay, you find the right frequency. Penetrating glass or a plastic bag, you can find frequencies that work. But really solid surfaces almost seems like magic. Let's see, where am I here? Okay. Next slide. Here we go. Well, what else can you do in the radio? Jupiter. Jupiter has radio emissions. They're generated by the interaction between the huge, massive Jovian magnetic field, which by the way, can stretch out past the orbit of Saturn, that's 5 AU, and the plasma that is generated from Io, from volcanic activity, which kind of circles Jupiter along magnetic field lines, and that's called the Io torus. As Io moves through Jupiter's magnetic field or magnetosphere, it creates electrical currents that generate powerful radio waves. Why is this happening? Because charged particles from Io's volcanic eruptions spiral around magnetic field lines, and as they do that, they're accelerating. Anything moving in a circular pattern is accelerating. An accelerated charge, as we know from the physics studies, Michael Faraday and Maxwell and so on in the late 1800s, generates electromagnetic radiation. So let's see. Now I just went off on a tangent. Sorry. This conceptual image up on top here shows the radio emission pattern from Jupiter. And here you see Io on the left, and you see the kind of darker lines, which are the Io torus in more kind of yellowish red colors. These multicolored lines represent the magnetic field lines that link Io's orbit with Jupiter's atmosphere and magnetosphere. The radio waves emerge from the source, which is located at the line of force in the magnetic field, and they propagate along the walls of a hollow cone, a gray area that you can see in this top image, with that gray cone slightly to the left. We also have in orbit around Jupiter, Juno, which can receive this signal when Jupiter's rotation sweeps that cone over the spacecraft. And in the same way, kind of like a lighthouse beacon shines briefly upon a ship at sea. So Juno's orbit is represented here also by this white line that is crossing the cone, kind of on the top part of this gray cone. On the bottom, we see an image of Jupiter. This is actually two images of Jupiter, both taken by the Hubble Space Telescope. The brownish, whitish image is an image taken in the visible part of the spectrum, where you can clearly see Jupiter's belts and zones and its shear forcing from its fast rotation. But you can also see on top Jupiter's aurora, and that is Hubble looking in ultraviolet frequencies. And this is, again, material from Io volcanism that is being driven down into Jupiter's atmosphere, colliding with hydrogen and producing an ultraviolet glow. Every planet in the solar system, every planet has some sort of aurora. And of course, it's strongest in the planets that have global magnetic fields. Last slide.
400 kilowatts of radio power. Blimey.
Well, astronomical objects that have changing magnetic fields can produce radio waves, and we talked about that a few moments ago. There's a radio astronomy instrument called WAVES on the WIND spacecraft. WIND is a NASA heliophysics spacecraft that records daily bursts of radio waves from the sun's corona, and from planets in our solar system. The data pictured here show emissions from a variety of sources, including radio bursts from the sun, where solar bursts from flares and coronal mass ejections span megahertz to gigahertz frequencies, revealing magnetic reconnection and particle acceleration. From the Earth, you can see evidence of auroral kilometric radiation from polar auroras. This is Earth's strongest natural radio emission, and it's detectable from space, but not ground-based due to ionospheric blocking. And even from Jupiter, as we just mentioned, Jupiter's ionosphere has wavelengths that measure about 15 meters in length, and Jupiter is the brightest radio source in the night sky. The only thing that's brighter is in the radio is in our solar system is the sun. So the far right part of this graph shows radio bursts from the sun caused by electrons that have been ejected into space during a solar flare. And these electrons are moving at about 20% of the speed of light. So here, those are some ways that you can explore the solar system, both in active radar and passive radar or radio, to see things that are absolutely impossible to see in other wavelengths. And I will end it there.
Thank you very much, Lou.
Mhm.
Well, that brings us to the end of our special tonight on radio astronomy, but not the end of the program. We've got more to come. So thank you guys for your contributions. And we hope, viewers, that you enjoyed that and perhaps learned something from it. And we will, of course, as always, keep you informed, keep you abreast of all the latest developments in radio astronomy. And it's got a golden future ahead of it, especially with the SKA coming online in 2 years. So there we are. So what we're going to do now is to move on to our regular features. And what we're going to do now is first of all go to Roger for our weekly look at the night sky. So take it away, Roger.
Okay, everyone, here we are back to normal service for this moment. Okay, so we're heading through the middle of November now, and we're working our way from the last quarter up through to a new moon in a week or so's time. So not too much moon glow in the night sky, fortunately. And looking south, we are now experiencing the last remaining parts of the summer triangle as we gradually work our way into the winter constellations, which are now gradually wearing their way up. And amongst the constellation of Gemini, we've got Jupiter there, blazing away. But everyone's favourite constellation is probably Orion, and that's coming up. That's coming up quite nicely. So almost as soon as it's dark, we can start to see the Pleiades coming up through the skies on the eastern skies. So we've still got Saturn over in the southwest. So we've still got two nice large planets to observe, should you so wish to. And just before sunrise in the morning, we've got Venus, which is nicely available. But I've got this later after sunrise, just to give you an indication that we've got Mercury and Mars the other side, about the same distance away in the sky. Although they will be rather difficult to see once we get near to sunset, because they will be roughly about the same altitude as the sun as it comes down. So it will be a challenging and very close to the sun for any safe observing, unfortunately. But if you want to, there we go. We are going to be having some northern Taurid meteors coming up through in the latter part of next week. So that's the legacy of Comet Encke. So we can attribute those to that comet. So there we are. So it should be quite interesting. But we've got Mars and Mercury, as I said earlier, fairly close together in the sky. But they will be a challenge, unfortunately, with the relatively close to the sun. So it might be probably best not to try and dazzle yourself with that. But we're hopefully going to get to see some Leonid meteors as well. And that's from Comet Tempel-Tuttle. Try saying that 3 times after a pint of brandy.
Yes.
Yeah, so some opportunities there. So we've got Uranus takes center stage, eh? So it's going to be opposition coming up soon, and not that that will make much difference to the apparent size due to its distance and size of the planet being too far away for us to get a good, decent view. But unless you're really lucky with a large aperture, obviously aperture envy again.
Yeah.
There we go. To get anything, but you can be lucky and get to see its color anyway with even a pair of binoculars. But obviously you obviously want to try and see a disk and maybe some of the moons as well. But there we go. So we've got Venus there in the morning, and we've got Jupiter coming up nicely, drawing the coming hours of darkness after sunset. So we will be getting to see two fairly bright planets either side of sunrise and sunset. So we've got we've just repeated that anyway. So okay, so we've got a gallery this week. Not a very big gallery, but welcome to all those that have managed to contribute. And we've got the first one from Jerry McTaggart. And this was done with his Sea Star, and that was on the 6th of November in the Whirl. And we've got a combination of some images of the east side, west side, and a sort of central view here with his Sea Star S50.
Pretty damn good. Yeah.
On that sort of note, Dwarf have now brought out, or about to bring out, a mini version.
Oh, really?
Did you know that? And you can almost slip it in your pocket. It looks very cute. But,
wow.
More on that later on. But there are some initial responses that it's absolutely amazing for imagery.
Wow.
Anyway, I digress.
Yeah.
Anyway, we've got Jerry DeLay, and he's done the Tadpoles Nebula in Auriga with his 100mm Esprit telescope, 45-minute exposures, and here we go.
Oh wow!
And we see the tadpoles on the right-hand side.
Yeah.
Swimming towards the centre.
Stunning stuff. Well
Very
done.
good. He does well, that man.
He does.
He does.
Well done, Jerry. That's fantastic.
Right, and we've got Michael Murphy, who's still down under, and he says, in answer to your question from last week's show, I haven't moved to Australia, but I'm taking an extended holiday here, where he's going to be back in the Northern Hemisphere in January. So he's spending about 3 months out there.
Wow.
There we go. So
yeah, Sandra says there's supposed to be a Sea Star Pro coming out in January.
Yeah, there's talk of a 70mm aperture on that version.
Oh, that's going to be the one.
Well, I don't know how big that might be, because I thought they were supposed to be more conveniently compact for doing things like outreach and just generally taking out and putting down. So it'd be interesting to see the size and weight comparison of that new version which will be coming out.
Yeah.
But there we go. No doubt they'll sell like hotcakes as well. So we got some nice groupings of sunspots there to come through, and obviously we've had a very big CME, which I've been told that Thursday, Friday might be worth looking out for, providing you've got any chance of any clear skies.
Yeah.
BBC weather we're hinting about tonight, maybe.
I know, but there is talk of another arrival coming in the next few days as well.
But we've got heavy rain at the moment here.
Yeah, and it's getting colder next week as well.
Yes.
So we've also got some of my lunar pictures that I took over the weekend. And
nice. Very nice.
As you can see here. And I
Wow.
got in closer with the image on the right-hand side. Obviously, when you've got a waxing or a waning gibbous moon, you've lost a lot of the detail further on round. So you get more detail and definition on the terminator areas there. So to focus on. So that's what I did with that. And that's what we've got for this week on the gallery.
Thank you very much. Yeah, so there we are. So thank you, viewers, for sending in your images as always. And don't forget, if you would like to send your images into the gallery, then just attach them to an email, one image per email, please, and send them to a gallery at spaceoddities.space. So there we are, simple as that. And you will be featured not only on our Tuesday gallery, but you will also have your own little gallery on our Space Oddities website. Now, I need to just mention this, actually. We do have a technical problem with the gallery on the website at the moment that suddenly popped out of nowhere. I haven't managed to solve it yet, but I'm working on it. So I hope within the next few days to solve that problem and have the gallery up and running. At the moment, I don't think you can actually have a look at your photos or anybody's photos, although you can see the thumbnails of them. But I am working on it and looking for a solution. So I'm.
There we are.
Well, lost our fearless leader.
Oh, there he is.
Yeah, there we are. Yeah, we're having a few dropout problems this evening with people coming and going. So apologies for that. I'll have a look at the technical report after, see if I can see what's wrong. But apologies, viewers. We keep periodically disappearing as if we were Time Lords. As far as I know, none of us are.
No.
So,
I wonder if this is how it happens at NASA. You're just on some telecon and then you're just not
Gone.
there anymore.
Yeah. So apologies for any technical problems. Circumstances beyond our control, as they say.
As they say.
Yeah. What we're going to do now is time for Constellation of the Week. Now, Mike,
Woo!
rather poorly the last few weeks, and we're glad to see you with that smile back on your face. Stupid though it is, and we're glad to see you back in rude health, Michael, to do the Constellation of the Week. So,
Yep.
Turn things over to you now for Constellation of the Week.
Okay, I'll just show that. Can
There we
you
are.
see
Thank
my
you.
screen?
Yep.
Oops.
Kenneth Minor.
That's what I wanted. Okay, this is the constellation of the week, and it's Canis Minor, also known as, or translation to the Lesser Dog. So Canis Minor is just a small constellation, and it has been known since antiquity, catalogued by Ptolemy in the 2nd century. So let's zoom on in this on here, just to show you the constellation. Just 2 stars, Alpha and Beta, make up the constellation. Just the 2 stars are joined, although all the stars are Gamma, Delta, and so on.
You say they're joined, Michael. That line isn't really there, you know.
Yes, I know.
Okay.
By the constellation lines.
Oh, I see.
How do you get a dog out of this? I'm just,
Yeah, I know.
Yeah.
But this is
right
another.
down. I just can't.
This is another representation of it. And although it's a picture of a dog, it's still just the 2 stars just make up the belly of the dog, which could be anything.
I suspect that how they got a dog out of that was by smoking lots of hashish in the desert. To be quite. So
yeah.
How real astronomy is done.
This is a location map to find it quite easy. Well-known Orion to the right there, and Sirius and Canis Major down below. And just move to the left. It's, as Roger said, Orion is coming up in the night sky very shortly, and so will Canis Major and these other constellations, of course. So using the
try to outdo yourself in picking the smallest constellation.
Okay, right. So just use the 2 bright stars at the top of Orion to draw an imaginary line from Orion over to the left to find Procyon, the Alpha Canis Minoris, and the constellation itself. That's just another artistic impression of what these representations are supposed to be. And this is another drawing from antiquity. There's Procyon, the main star, and yeah, it's quite elaborate. quite an elaborate dog on this one, really, as well. Yeah. This is a work by Johannes Bode in his 1801 work, Uranographia. Excuse me. Okay. This is a pictorial view showing the Orion with the nebulosity around the belt and the sword. And they, if you use an imaginary line to find Canis Minor. This is Procyon, the brightest star, which also forms one corner of the Winter Triangle asterism. The other corners being Sirius in Canis Minor and Betelgeuse in Orion. That's known as the Winter Triangle asterism. Stars. Canis Minor has only 2 stars brighter than magnitude 4. Procyon Alpha Canis Minoris is an F-type main sequence star, 11.5 light years away. It's the 8th brightest star in the sky, now known as Procyon A. The star also has a companion star, a faint white dwarf of magnitude 10.7. And this is on a drawing showing the relevant sizes of the 2 stars. The existence of Procyon B had been postulated by German astronomer Friedrich Bessel as early as 1844.
Wow.
Mm.
Quite a size difference there.
Yeah. So Beta Canis Minoris, or Gomesia, has a magnitude of 2.9. Gomesia is a blue-white main sequence star. Although fainter to Earth observers, it is much brighter than Procyon, and it is 250 times as luminous and 3 times as massive as the Sun. Gomesia is classified as a shell star or Gamma Cassiopeiae variable with a maximum magnitude of 2.84 and a minimum magnitude of 2.92. It is surrounded by a disk of gas, which it heats and causes it to emit radiation. The Gamma Canis Minoris is an orange K-type star, a giant that is part of a binary system, and it has an apparent magnitude of around 4.3, and that's gamma points located by the arrow there. Johann Bayer used the Greek letters alpha to eta to label the most prominent 8 stars in the constellation, designating the 2 stars as Delta, named Delta 1 and Delta 2. John Flamsteed labelled another star in the group as Delta 3. This is the group that is referring to here to the Delta stars in Canis Minor.
Right.
Bit strange.
Yeah.
Okay.
Well, each to their own, I guess.
Yeah. Deep sky, not a lot going on really. This is red hued cloud of gas is named Abell 24. It's a planetary nebula in the constellation. That's not much else known about that really.
Right.
But it is rather faint. So
nice photographic target, definitely.
Yeah. And another faint deep sky object is a spiral galaxy, NGC 2485, which is approximately 233 million light years away. So that's the.
What's that on the right? PGC 21346.
Good question.
Is that a galactic merger? It looks like it might be.
Oh, it could be.
Yeah.
Okay,
thanks.
All right. Okay. Sorry about that.
Right.
Regarding exoplanets to date, there are no discovered exoplanets within the boundaries of Canis Minor. and that is that presentation. Thank you.
Thank you, Michael. Thank you very much indeed. So, Michael, let's get this straight. So you chose a constellation with 2 stars, 2 fairly unimpressive deep sky objects. Nothing much to talk about, really.
Well, no constellation should be, unnoted.
Well, yeah.
Look at all those constellations behind you, Michael. You could have picked any one of them.
Yeah. Yeah. And so, continuing on your quest to talk about the smallest constellation in the least amount of time,
Yes.
we're going to have to send you back to Constellation of the Week school, I think. Mind you, the professional on your left or on your right, depending how you look at it, I mean, he always goes for giant sprawling constellations with dozens of deep sky objects.
Absolutely, yeah.
Yeah.
Although I did Aquilius the other week, and that was quite a small one, so I took that one from Michael.
Yes, I had that. I had that one in my site.
See me after class, Michael. Right, okay. All right then. So just to finish off tonight, yes, it's that time again. We're going to delve into the nether regions of social media, and we're going to have a look at Einstein of the week. I haven't got that many for you this week, just a few, but these, well, you'll see. It's never ceases to amaze me what people on the internet, by extension, people generally, have to say about the universe. So the first one, you sure about that? Blue Origin's New Glenn rocket, NASA's first Mars mission. Did you know that? NASA's first Mars mission is launching.
Finally. That's such a relief.
Finally. So there we are. Oh, by the way, thank you, viewers, for joining us on Sunday for the launch of New Glenn. We covered that live, but it was scrubbed due to a lot of factors. Bad weather was a main factor. Cumulus clouds are the big danger because they can generate a lot of electrical activity and thunderbolts and lightning strikes. And there was a lot of cumulus cloud around. Also, some cruise ship captain decided he'd give his passengers a ringside view of the launch of Blue Origin's New Glenn and sailed into the maritime exclusion zone, which delayed the countdown quite considerably. And in the end, they got too close, and they had a target of 1 minute before the close of the launch window, and they didn't make it. They were meant to launch last night. That didn't happen, and it's now happening tomorrow night. So join us tomorrow night live for the launch of Blue Origin's New Glenn, sending those 2 NASA spacecraft, the Escapade probes, to orbit Mars. And we go live at 8:30 UK time tomorrow evening on the channel. So please join us for the launch of New Glenn. Let's hope it happens. Anyway, moving on. No, it's not. First images from Vera Rubin, the largest telescope ever built, reveal millions of galaxies. It isn't the largest telescope ever built. It is the biggest digital camera ever built, but it's certainly not the largest telescope ever built. Yet again, one of these 10 a penny astronomy pages on Facebook that can never seem to get the facts quite right. But yeah.
Hey, it sells newspapers, okay?
Well, yeah, it sells something, and there are so many of them on Facebook. I'm sure the people set them up in good faith to talk about astronomy, but their quality control and their editorial control and their proofreading is non-existent a lot of the time. So big error there. Oh, I think this is the next one, the last one. This is funny. It goes back to an old sort of meme on social media, going back a few years. If you look at the map at the top, I don't know whether you can see this. Somebody said that basically the Japanese could not have attacked Pearl Harbor because of that distance that they had to travel around the Earth. And that was that's been going around the internet for years, that one. And but it cropped up again recently, and somebody said it can't go the other way. And the answer to that was no, the Earth is flat. This is basic knowledge. So there you are. So
I need
there we
to go
are.
back to
Yes,
school.
the bottom actually said, I also preach the logic that planes can't fly over land. Well, if the Japanese had flown over land, I think quite a lot of them would have been shot down in various countries. But anyway, somebody's saying the Earth is flat, and of course it's basic knowledge, as we all know. So that's all I've got for you for Einstein of the Week this week.
Amazing.
I am, of course, constantly keeping my nose to the grindstone or something to find these things for you, and I hope you enjoy them. So there we are. Now, next week on Space Oddities, let's talk about next week. There have been a lot of quite interesting discoveries about Lou's baby recently, Titan, and including, if you remember when I talked about volcanoes of the solar system last week, I've now had to expand the presentation because there's been some recent fairly hard evidence that Titan has active cryovolcanism. So really, really interesting stuff. So we've asked Lou if he wouldn't mind talking about all these latest findings about Titan.
What?
Next week.
Oh,
Yeah.
okay. Yes. Yeah. Right. Sure. No
We
problem.
talked about this. Yes, we did. And yes, we're going to talk about Titan next week, which I'm sure Lou will look forward to.
Made
And
my day.
we will tell you all about Titan, which is the most amazing, one of the most amazing worlds in the solar system. Lou would probably say the most amazing, but
It is.
yeah, it is.
Objectively, just objectively.
Objectively, yeah. So I would put Titan, well, probably a little bit above Enceladus and Europa, but I think all three worlds are intensely interesting. But there's a lot more to talk about with Titan, I think. And there we are. So join us next week where we'll be looking at Titan and some other stuff as well. I'd like to thank Dave for coming along this evening. Lovely to see you, Dave. And I hope you've enjoyed yourself, and I hope you'll come back soon.
Yeah, thank you. Thanks for inviting me again. And yeah, I had some technical difficulties in the middle there, so I kind of dropped out. But no, yes, thanks.
No problem. Well, you know you're welcome, and any Tuesday just drop in. You don't need an invitation. You're more than welcome. So
come next week, Dave. You're more of a surfaces guy than I am. I don't deal with boring. So.
Sounds good. Okay. Yep, I'll be there then. Thank you.
I mean, if you just if you were to meet a lady in a bar, would that be your chat up line? I'm a surfaces guy, because that sounds pretty cool to me.
What does that mean?
So there we are. Yeah. So yeah, come back and see us, Dave.
That's a cleaner, isn't it?
Sorry.
That's a cleaner, isn't it?
Yeah. Surfaces. Yeah. Well, years ago, not long after I left university, and I left university in the middle of a recession in Wales, which is not the best place to be at the best time. And I ended up just to earn some money working in as our American friends would say, a gas station. And, going to parties and meeting ladies. And I didn't want to admit that I worked in a gas station. So I used to tell them I was a fuel injection engineer. And, they say, what sort of vehicles do you work on? Well, all types, really,
Did it work?
No.
No.
There we are. So there we are. Okay. All right, then. So we'll bring things to a close. Titan next week, and we'll come up with some other stuff for you. I'd like to thank all of you for being here. Don't forget to like, subscribe, and comment, please, because it really helps us. Thank you all for being here. And thank you for the donations. And we will see you next week on Space Oddities. But don't forget, we'll be live at 8:30 UK time tomorrow evening for the fingers crossed launch of Blue Origin's new Glenn, sending those important spacecraft to Mars. And also, of course, it will be Blue Origin's second attempt to land their first stage on a barge, a la SpaceX. So we'll see whether that comes off. So it'll be quite an exciting time, quite an exciting launch. But the important thing is getting those spacecraft to Mars. But we will talk about those spacecraft tomorrow evening before the actual launch. As I said, we go live at 8:30 UK. Hope to see you there. If we don't see you there, have a fantastic evening, fantastic week, everybody. Look after each other. And from all of us at Space Oddities, a very good evening to you. Bye-bye.